Right, so what I'll do here is I'll do a review of what expected value of a random variable is, right? Okay, so let's start with the case of a discrete random variable, right? Okay, so if I have a discrete random variable with probability mass function, right, which is probability x is equal to small x over here, right? Okay, and your probability mass function for a discrete random variable is either given by a formula or as a table like this over here, right? Okay, so if I have a probability mass function for discrete random variable, what the expected value of the random variable x is denoted as e of x, right? Also denoted as mu here, right? It is this sum over here, right? Now what you're doing is you sum in over all possible values of the random variable. So for this example over here, the possible values for the random variable would be 4, 5, 6, 7, 8, and 9, right? Okay, so you sum over all possible values of your random variable and you multiply the value by the associated probability here, right? Okay, so let's just look at this example, right? This example has two parts. We will get to part two in a little while, right? But let's focus on the first part, right? Okay, so we were given that the number of cars that go through a car wash between a fixed time interval between 4 and 5 p.m. on Friday, right, has this probability mass function, right? So the probability of 4 cars passing through the car wash in the time interval is 1 on 12. The probability of 5 cars passing through is 1 on 12, and so on, right? Okay, and they asked me to get expected number of cars passing through the car wash for a given time period, right? So we want to get expected number, so we're going to be using expected value, right? I'll explain a little more as to how you're going to interpret expected value, right? But let's just actually get familiar with using this formula here, right? Okay, so expected value of x, right, is you sum in over all possible values of your random variable, right? And then you take your value of your random variable and you multiply by the associated probability, right, for each value, right? Okay, so in the case you'd have x is equal to 4, right? The probability when x is equal to 4 is a half, right? When then here you have 5 times probability x is equal to 5, and it's 5 times the 1 on 12 over here, right? And then this one over here, it's x times probability x is equal to x, right? So the value over here is 6, and the probability x is equal to 6 is equal to a quarter, right? And you go ahead like that until you get, say, the last value here, which is last possible value for the random variable x over here, which is 9, and then you have 9 times the probability x is equal to 9, which is 1, 6, right? So you get this expression over here, and really you just work it out, right? And when you work it out, you get an expected value of 6.833, right? Now you want to notice that this expected value, right, is taking a value in between the 4 and the 9 over here, right? So that's one thing you could notice. Okay, so let's consider this example that we did last week, right? We had a fair coin that we gonna toss 3 times, right? So the possible outcomes, you're going to have 8 possible outcomes in your sample space, and that would be these 8 outcomes over here, right? And in the sample space S, right? Okay, and in this example, what we have, we had 2 random variables which was defined on this sample space. One is the number of heads on the first toss, right? And then second one was y was the total number of heads, right? Okay, so what we're doing today is we're really just focusing on one of these random variables here, right? Really, what I want to do is I want to interpret what expected value is, right? Okay, so I'm focusing on random variable x over here, which is number of heads that you're going to get in the first toss, right? So we're looking at this random variable x over here, right? Okay, so what are your possible values of your random variable x here, right? Well, remember what x is, right? X is the number of heads on the first toss, right? Okay, so all you're really doing is, well, you're looking on your 8 outcomes, you're looking on at your first toss over here, right? So for this one here, when you have uh, 3 heads, right? On the first toss you have a head, right? So the number of heads that you have on a first toss over here is 1, right? So the value of x for this for this outcome over here is 1, right? Similarly, the value for this outcome over here of your random variable x is 1, right? However, for this one over here, right, the value of a random variable here, the number of heads that you have on the first toss is 0, right? So the value of the random variable over here is 0, right? So let's consider this question here, right? So we have a fair coin tossed 3 times, so same setup, right? Set of possible outcomes. You have 8 outcomes already. X is the number of heads obtained on the first toss, so it's the same X as what I had before, right? And what I want to get is I want to answer this question, right? So what's the average value of X that I will obtain, right? If I do this experiment a large number of times, right? And by large, I mean, say like 1,000 or so, right? Okay, so let's see if we could figure that out, right? What would be your average value of X that you would get if you did this experiment, say 1,000 times, right? Okay, so what's the, first of all, to work this out, well, we'll need the PMF of the random variable x, right? Now, what are your possible values for the random variable x, right? Possible values would be 0 and 1, right? So I have it over here, right? Now, what's the probability of, say, getting x is equal to 1, right? Well, you see what's happening. There's a couple of ways you could work this out, right? The case when x is equal to 1 would be these 4 cases over here, right? So you have 4 outcomes in the event when x is equal to 1, right? And because these outcomes are equally likely, right, the probability of getting x is equal to 1 is 4 out of 8, which is a half over here, right? Okay, and that's probably the best way to look at it, right? And then x is equal to 0 would correspond to these 4 cases over here, right? And the probability of obtaining this event with these 4 cases would be 4 out of 8. So you're going to get a half over here as well, right? A next way to look at this is really you're just looking at what's happening on the over here for this random variable, right? All you're really looking at is what's happening on the first toss, right? So on first toss, you're gonna get a 1 if you get a head, and you're gonna get a 0 if you have a tail, right? So essentially, either you get a head or a tail, and if it's a fair coin, the probability of getting the head is a half, and then the probability of getting the head over here, which would mean when x is equal to 1 would give you a half, and the probability of getting a tail, right, which is not a head, right, in that case you'd have x is equal to 0, which is a half. Anyway, so this is the PMF of this random variable x, right? Now, what we want to do is we want to figure out, well, okay, so if I do this experiment, one time, I will probably get, say, I'll get one value, right? Let's say I get a value 1, right? Now, if I do the experiment again, I could, let's say I get the value 0, right? And if I do the experiment again, I'll get a value 1. And if I do the experiment again, I could get a value 1 again. Do it the 5th time, I get a value 0, right? So each time you do it, you're going to get a certain value, right? Now what you want to do is you want to get the average of those values, right? So let's say if we do it 1,000 times, right? What do we expect to happen, right? Well, what we expect to happen is based on the probabilities that we have over here, right? If we do this experiment 1,000 times, right, then given the fact that the probability that you get in a result 0 is a half, right, means that you expect, right, that you're going to get the value 0 500 times, right? And similarly, you expect to get, if you do the experiment 1,000 times, you expect that you're going to get a value 1 500 of the times, right? Okay, so notice over here, this is expect, right? If you actually do the experiment 1,000 times, right, you probably wouldn't get exactly 500 over here for when x is equal to 0, right? But you'd get something that is very close to 500, right? Okay, so that's if the coin is fair, right? But what we expect, right, and based on the probabilities over here, is that if you do the experiment 1,000 times, you expect to get the value of 0 500 times, right? And expect to get the value of 1 500 times, okay? Right, so we do the experiment 1,000 times, you're gonna get, we get 0 500 times, you get 1 500 times. And what's my average value, right? What's the average value of the outcomes, right? Well, what you need to do is you need to add up all your possible outcomes, right? So you're gonna get you have you get 1 500 times, so that's 500. 1 plus 1 plus 1 500 times is 500 times 1. And you're gonna get 0 500 times, so that's 0 plus 0, so on 500 times, and that's 500 times 0, right? So the total, if you add up all the values that you get, right, would be 500 when you work it out. 500 times 0 plus 500 times 1 is 500, right? Okay, and the average value of that, right, would be this over here, your sum over 1,000, right? Okay, so let's actually keep working this out over here, right? I'm gonna rearrange a little bit, right? So here I have a common denominator, which is 1,000, but I can write this as 500 over 1,000, right? And I can write this as 500 over 1,000. And this is 500 over 1,000 times 0, 500 over 1,000 times 1, right? And this 500 over 1,000 is a half, and this 500 over 1,000 is a half over here, right? Okay, so what I get is that my average value is going to be a half times 0 plus a half times 1, right? And I'm going to rearrange this slightly over here, right? Okay, anyway, so once I get to this point, right, let me just actually work out what my average value that I would get, right? The average value that I'm going to get here is, if you work this out over here, is just going to be a half, right? Right, so what I want to do is I want to tie this expected value, this average value that I get, right, which is a half, right? I want to tie it to the expected value, right? Okay, so that's why I rearrange like this. It's not really a big deal. A half times 0 is 0 times a half, and a half times 1 is 1 times a half, right? Now you want to notice how I wrote this over here, right? This is value of the random variable x, right, which is 0, right, times the probability x is equal to 0. And this is value of the random variable 1, right, when times probability x is equal to 1, right? And this is a sum over here, right? So what you're doing is you sum in over all possible values of the random variable, which is fairly simple in this case. You only have two possible values, which would be 0 and 1. And you consider in this sum over here, and this sum you can write in summation notation like this, right? And this over here, this is your definition of expected value, right? Okay, so working this out over here is actually just working out expected value, right? So the point I want to make over here is that what expected value is, right? Expected value is, you could approximate, right? If you take your experiment and you do it a large number of times, say like 1,000 times, right? And you take the average values of the random variable that you get, right? Then that average value over here would be equal to expected value, right? Here, this is I have this as the average value actually worked out to be exactly equal to the expected value, right? But in reality, the average value that you would get would be close to the expected value, right? But if you do the experiment, say 1,000 times or 10,000 times or a million times, and so the average value that you would get closer and closer to this expected value over here, right? So it would informally, it will converge the average value that you would get if you increase the number of times that you do the experiment. The average value would approach your expected value of x. Okay, so if we look at this example here, right, we have number of cars is a random variable x, right, and we just saw this example. Number of cars x is the number of cars passing through the car wash at a certain time interval on Friday, right? And this random variable is a discrete random variable with a PMF over here, right? And we just looked at this example, right? Okay, so this is random variable x over here, right? And now what we have over here is, as I said, this question had two parts, right? and random variable x is the number of cars, right? But your second part over here is that 2x minus 1 is the amount of money paid to the attendant by the manager, right? Okay, so you have the attendant say doing his job on washing the cars, right? And the amount of money that he gets, right, is based on the number of cars that passes through the car wash, right? Okay, so he gets let's say for each car he will get twice $2 for each car, right? So that's how you have 2x over here, right? And for some reason it's minus 1, right? Probably, I don't know, he has expenses or something like that, right? But anyway, so the amount of money he gets depends on this big X over here, right? So the amount of money that he is going to be getting, right, is actually a function of this big X over here, right? So this 2x minus 1, which I denote as g of x over here, this is a function of your original random variable x over here, right? In other words, you take this random variable x over here and you modify it in some sort of mathematical way, right? Okay, so it could be x squared, it could be well, 2x minus 1, it could be other things, but in this case, the function of the random variable is 2x minus 1, right? Okay, so I just gave you an example of a function of a random variable, right? If you have a random variable x over here, function of a random variable, you essentially modifying it, right, in some sort of mathematical way, right, like this. So you could have x squared, you could have 2x minus 1, right? Okay, but more precisely, what a function of a random variable is, if we want to, well, let's be a little formal over here, right? So what is a random variable, right? A random variable is a function on sample space, right? So this over here is an example of a sample space where I have 8 possible outcomes, and this x over here is a function on this sample space over here, right? So possible values of your function would be either 0 or 1 here, right? So this is an example of this is your s over here, right? And this x over here is mapping from s to the real numbers over here, right? It may not seem like the real numbers, but why I have 0 and 1 over here is to really indicate the values of the random variable, right? But this here is map from s to r here, right? Okay, so this is our random variable, and now what we have is we're going to have some function, right, such as the 2x minus 1, right? So we're going to have a function g over here, such as this 2x minus 1, right? And what we do is we're now going to consider a composition, right? So the 2x minus 1 is a function from r to r, right? So over here, the g over here, this is an example of a g, right? And what we want now is composition, right, of your random variable, which is a function from sample space to reals over here, right, with this new function small g, right? Now, once you do that, right, once you form this composition, right, this composition is denoted as g of random variable x, right? And this, in fact, is this composition over here denoted as g of x. This is a random variable, right? Because what you want to notice is if you look at the composition, it's a function from sample space over here to the reals, right? Okay, so that is how you would formally consider this. If you have x being a random variable, such as this example over here, then g of x is also a random variable, right? Okay, and when you form in this g of x over here, right, what you're doing is, all you're doing is you're taking these values over here, right? So you're taking these values here, the 4, the 5, the 6, and so on, so the values for x. And then you form the g of x, right, which is the function of the random variable that's specified for you, right? So the g of x over here is 2x minus 1, right? So if for x you have value 4, right, then the g of x would be 2 times 4 minus 1, which is 8 minus 1, which is 7, right? And likewise, for the 5, right, 2 times 5 minus 1 is 9, right? So for your values of x over here, you form your values of g of x, right? But the probabilities over here would be the same, right? So x is equal to 4, form value g of x which is 2 times 4 minus 1, which is 7, right? But the probability is still this the same probability as the x, which is 1 on 12, right? And the reason why it's the same probability in this case is that this function g over here, this function 2x minus 1, right, which we have in our example, right? So this function over here, 2x minus 1, right? The reason why it's the same, right, is that this here, this 2x minus 1, it's a one-to-one function, right? So if I'm looking at the 7 over here, right, the 7 here, right, has a single pre-image under the map over here, G, which is 4, right? And that 4 over here, right, has a certain probability associated to it by actually going backwards, taking the pre-image under the random variable and considering the event over there, right, which had a certain probability associated to it, right? So that's really why the probabilities are the same, right? If the function g wasn't say one-to-one, it would probably be a little more complicated, right? Anyway, so in these simple examples over here, right, when your function g over here is one-to-one, right, this would be how you would get the PMF of this would be the PMF of random variable g of x here, right? Okay, so let's work out this problem here, right? So number of cars x that pass through the car wash between 4 and 5 on Friday has this PMF over here, right? We worked out part 1 already. Let's work out part 2, right? Okay, so the amount of money, the earnings by the attendant is given by g of x, this function of a random variable, which is 2x minus 1, right? And what we want is his expected earnings, right? Okay, so you could look at it this way, right? That if you have for the number of cars passing through the car wash has PMF, this PMF over here, which means that either 4 to 9 cars pass through the car wash, right, with these probabilities, right? And if you have these 4 to 9 cars passing through the car wash, each one, if 4 cars pass through, right, then his earnings would be 2 times 4 minus 1 coming from this 2x minus 1, right? And the probability of his earnings being 7, right, is 1 on 12, right? Similarly, if you have 5 cars, then his earnings would be 2 times 5 minus 1, which is 9, right? And the probability of the earnings in that case is 1 on 12, right? Okay, so the expected earnings of the attendant would be the expected value of this random variable g of x, right? Now you could work it out from this PMF table over here, right? But the better way to do this, right, is to use this definition, right, which would give you the same thing, right? The benefit over here is that you don't need to construct a separate PMF table to work this out, right? Okay, so you don't need to construct this separate PMF table. Really, you're just working with the same your original PMF table, but the only thing you're doing over here is you modifying instead of having values of x over here, you have value g of x over here, right? So for example, if this is 4 over here, right, when the x is equal to 4, the earnings would be 2 times 4 minus 1, which would be 7, right? Okay, so to get expected values of a function of a random variable, it's better to use this definition here, right? Rather than try to construct the PMF for the function of the random variable g of x, right? So let's actually just work it out here. Okay, so what we want is the expected value of this random variable 2x minus 1, which represents the random variable for his earnings, right? Okay, so expected value of 2x minus 1, right? You're using your formula here for expected value of the function, the random variable, right? And this g of x over here is coming from the function of the random variable here, right? So this is the random variable 2x minus 1, and the values it would take would be 2 small x minus 1, right? So notice this here is g of small x, right? So random variable, the function of the random variable is g of big X, and the g of the big X is 2x minus 1. And the g of the small x is 2x minus 1, right? Okay, and once you have this set up over here, what you're doing is you sum in over the values of x, right, from your original PMF, right? So you're putting in, say, x is equal to 4 to start off with. When you put in x is equal to 4, you're going to get 7 times the probability. Notice over here, this is x here, right? So you're on probability x is equal to 4, and probability x is equal to 4 is 1/12, right? Okay, so calculating the expected value of the function of the random variable, where you use the function is over here, right? So you're changing the value, you're changing the x over here to the g of x, right? But everything else remains the same, right? So for each value of x over here, you calculate the corresponding value of g of x. So for example, this 5 over here, you're going to get 5 times 2, which is 10, minus 1, which is 9, right? But then you want probability for the x is equal to 5, which is 1/12, right? Okay, so that's how you do that, right? Okay, so you do it for each value of x here, right? You calculate the corresponding values of g of x. You use the probabilities here from the original PMF table. You write out your sum, and then you work out your answer, which is, in this case, is $12.67. Right, so for a discrete random variable, we have a formula for the expected value of x, right? What you do is you sum over all the possible values of your random variable. And the terms in your summation would be the value of the random variable times the probability that the random variable over here is equal to that value, right? So in other words, the summation of x times probability x is equal to x, right? Okay, so this is expected value if in the case of a discrete random variable. In the case of a continuous random variable, what you have is you have an analogous formula, right? Okay, so here what you're doing is you're taking the value of the x, right, and you're multiplying it against the PMF, right, corresponding to the small x, right? The value of the PMF corresponding to the small x. Anyway, so it's small x over here times the PMF, right? In the case of a continuous random variable, what you're going to do is you're going to take the small x over here and multiply it now against the PDF here, right? Which is denoted in this case as f of x here, right? Okay, so over here in the case of discrete, it's small x times PMF. And in the case of continuous, it's small x times PDF over here, right? Here, what you do is you sum in over all possible values of the discrete random variable. And here, what you're doing is, again, you sum in over all possible values of the continuous random variable. But continuous random variable takes real values, right? And all possible values would, in fact, be from minus infinity to infinity, right? Some of them may be 0, right? But to start off with, this would be how you'd get all how you'd sum over all possible values, right? If some of them if the probability density function is 0 outside of a certain interval, then this would simplify for you, right? Okay, alright, so for example, this continuous random variable x over here with a PDF, right? And notice the PDF is only non-zero between 0 and 3, right? Okay, so we want to get expected value of it, right? So expected value of this continuous random variable, according to my formula, it's x times the PDF of x, right? And you integrate between infinity and minus infinity, right? The thing is, when you're integrating between infinity and minus infinity, right, this function is only non-zero between 0 and 3, right? So this over here will reduce the integral between minus infinity and infinity. Would reduce the integral between 0 and 3, right? So if you want the possible values of your random variable x over here, really you just lie between 0 and 3, right? So what you're doing over here is you're integrating over your possible values of your random variable 0 and 3 here, right? And then this is just x times your PDF over here, right? You get 2 9ths on x squared, and you integrate between 0 and 3, and you get the answer here, which is 2. Okay, so in the discrete case, remember that expected value of x is you sum in over all possible values of your random variable. and it's x times PMF, right? And for a continuous random variable, you're basically doing the same thing, but in a continuous sense, right? You take any possible values of x, you multiply it against the PDF now, and then you sum in over all possible values of x, right? And all possible values of x will lie between minus infinity and infinity, and we just saw an example that you can actually reduce that down based on what the PDF is, right? Okay, so let's consider now expected value of a function of a random variable. Right. Okay, so a formula in the discrete case for expected value of a random variable, right? This is what we used, right? You sum in over all possible values of x, right, of the discrete random variable. This g of x over here is a function of your random variable x. And in the formula here, right, for each possible value of the x, you calculate g of x, right, and then you multiply it by your probability here, right. So this x over here is coming from the original random variable. Your probabilities over here coming from the original random variables. What's changing is instead of using x over here, you use g of x, right? Okay, so this is the formula for expected value of a function of a random variable when the random variable x is discrete, right? In the case when the random variable is a continuous random variable, you have a similar formula, right? So for you're gonna take the g of x, right? You take your g of x, right? G of the small x. Here you're multiplying the g of the small x against the PMF. Here you're multiplying the g of small x against the PDF over here. Here what you're doing is you're summing over all possible values of the discrete random variable x. Here what you're doing is you're summing over all possible values of the continuous random variable, right? Okay, so the formulas are analogous. In this case, you have summation, and in the continuous case, expected value of g of x. You do it now by integration, right? Okay, so let's see this example over here, right? I have x is a continuous random variable with this PDF here, right? Notice the PDF. It's only non-zero between -1 and 2, right? Okay, and I want expected value of 4x plus 3, right? Now, to get expected value of the random variable 4x plus 3, right? What you're doing is you're taking this 4x plus 3, replacing the big X by the small x over here. So you have 4x plus 3 over here. And then now what you do is you multiply by your PDF, right? And the PDF is x squared on 3. Notice it's x squared on 3, but this is only non-zero between -1 and 2, right? So when you integrate everything outside of the -1 and 2 will drop off, right? So you get this over here. And then this is just normal integration. You multiply it out, right, to get 4x cubed on 3 plus x squared. And you integrate between -1 and 2 to get your value, your answer over here of the expected value of 4x plus 3, which is 8 here. So in the case of a single discrete random variable, if we have a function of that single discrete random variable x, right? If we have a function g of x over here, this is our formula for calculating expected value of g of x here, right? Okay, so notice here what you're doing is you're summing over all possible values of a random variable x here, right? And you take in g of x and you're multiplying it by the probability that the x is equal to x, right? Now you have a similar formula for the joint case, right? Okay, so if I now have x and y random variables, and let's first consider the discrete case, right? So I have x and y discrete random variables with a joint PMF, right? F of xy here, right? And I have now a function of the two random variables, x and y, right? If I want to get the expected value of this function of random variables g of xy, right, it's a similar formula to the single variable case, right? Here what you're doing is you're summing over all possible values of x, right? Here what you need to do is you need to sum over all possible values of x and y, right? So that's why you have this double summation here, right? And then it's instead of g of the small x now, it's g of the small x times y, right? Here it was g of small x times your PMF, right, for single variable. And here now this is g of xy times joint PMF over here, which is f of xy, right? Okay, so let's see an example of doing this, right? Let's working this out, right? All right, so I have x and y discrete random variables with this joint PMF, right? And remember, your joint PMF could be specified by a table, right? So, for example, over here, right? Let's say when when x is equal to 1 and y is equal to 0, the probability that x is equal to 1 and y is equal to 0 is just 9 on 28 over here, right? Okay, so this is a joint PMF of discrete random variables x and y. We talked about this already, right? What we want to do is we want to get the expected value of this function of the two random variables, which is g xy, right? So the notation over here is a little bad. You should have a comma over here, gx comma y, right? So, right, notation is a little off over here, but this is correct, right? The function of the two random variables, in this case, is the product x times y, right? And what I want is expected value of x times y, right? So in this case, the g of xy over here is xy, right? So I'm going to put xy, sorry, the g of xy, right? The g of xy is xy, right? So the g of xy over here is x times y, right? So if I want expected value of x times y, what I'm going to have is small x times small y over here, right? So this is what's going on over here to get the expected value of the function of the two random variables, which in this case is the product of x times y. This is you're going to be doing a double summation, summing over all possible values of the discrete random variables x and y, right? Here, this is the g of xy, where you use these are values, so you use the small letter x and the small letter y, right? And then you multiply by the probabilities that are coming from your table, right? So in this summation over here, right, you're going to have terms, you're going to have a term for each term in this PMF table over here, right? Okay, so what are your different terms, right? The first term is, well, when x is equal to 0 and y is equal to 0, right? So that case, x is equal to 0, y is equal to 0 would be 0 over here, 0 over here, and then probability x is equal to 0, y is equal to 0. So you're going to get 3 on 28, right? And then you're going to have this term in your table over here, which is x is equal to 1, y is equal to 0. So here x is equal to 1, y is equal to 0. And then you use the corresponding probability when x is equal to 1 and y is equal to 0, which is 9 on 28, right? And then you do that for all 9 terms in your table, right? I wrote it out over here, right? In this form, the first row of the summation is for these first 3 terms. Second row over here is for these 3 terms, and third row over here is for these 3 terms, right? Okay, so when you do your double summation over here, you effectively you sum in for each term in your PMF table, and this would be what you'd get, and then you really just work this out, right? Matter of fact, this is fairly simple to work out because the only non-zero term over here is when you have a 1 over here and a 1 over here, and you have 1 times 1, which is 3 on 14, right? So overall your answer for the expected value of x times y is 3 on 14. Alright, okay, and in the case of a continuous random variable, right, if we have a function g of x of a continuous random variable x, right, how we saw how we got the expected value of g of x, right, was taking the g of the small x, multiplying it against the PDF, and integrating between minus infinity and infinity, right? Okay, so this is in the case of a single continuous random variable, right? In the case of two random variables, right, two continuous random variables with a joint PDF f of xy over here, right? How we calculate the expected value of a function of the two random variables x and y, right? It's similar to what we did in a discrete case. What we're going to be doing is taking the function g of small x and small y, multiplying it against the PDF now, and then again summing over all the possible values of x and y, right? And in this case, summing in the continuous context is integrating, right? And summing over all possible values would be for y and x would be integrating from infinity to minus infinity and infinity to minus infinity, right? In other words, you're integrating over the entire xy plane. So let's see an example of using this formula here, right? Where we want to calculate expected value of a function of two continuous random variables with a given joint PDF here, right? So here I have two continuous random variables, x and y, with a joint PDF given as f of xy is equal to a quarter times xy, right? And notice this joint PDF is only non-zero on your rectangle. X going between 0 and 2 and y going between 0 and 2, right? So in other words, well, more precisely, it's a square, right? So square one corner at the origin, one corner at 2 at 2, right? Okay. And this is what the f of xy is on that square, right? Otherwise, it's equal to 0, right? Okay, so we want to get expected value of a function of x and y over here, right? So the function in this case is x squared y, x squared times y, right? Okay, so to get the expected value of x squared times y, what you're going to be doing is you're integrating that function, which is the x squared times y, against the PDF, the joint PDF, f of xy, which in this case is a quarter times xy. Right, you're integrating from infinity to minus infinity and infinity to minus infinity, but this joint PDF is non-zero only on the square, right, where x lies between 0 and 2 and y lies between 0 and 2, right? So the only place you need to integrate is over that square, because everywhere else the integral is 0, so that's what's going on over here, right? In this case, you're integrating with respect to x first and then with respect to y, right? Integrate and the limits of integration for the x would be just 0 and 2, and for the y it would be 0 and 2 over here, right? And now first thing we do over here is we multiply this out, so you're gonna get x cubed times y squared, and pull the quarter outside, and now you start integrating. Integrate with respect to x, you're gonna get x cubed on 4, x to the 4th on 4, sorry. And then you put in your x values, which are x is equal to 2 and x is equal to 0, right? So that gives me 16 on 4, which is just 4 over here, right? And when I put in x is equal to 0, I'll just get 0, right? So all I'm left with is just 4y squared, integrating 4y squared with respect to y between 0 and 2. And when you work that out, you get your answer over here, which is 8 on 3. Okay, so let's talk about variance now, right? So we saw what expected value of a random variable is, right? So random variable x, the expected value is, say you repeat your experiment a large number of times. Each time you do it, you get a certain value of your random variable, and you take the average of that, right? That is effectively what the expected value is going to be, right? So the expected value is the average value of a random variable if you do your experiment a large number of times, right? Okay, and that average value is where your probability distribution is centered, right? Okay, you'll see an example of that in a second, right? Okay, so here now I have what variance is going to be, right? What variance of a random variable is going to do is it's going to quantify the spread or dispersion of the possible values of x about that expected value or the mean, right? Okay, so as an example, consider these two discrete random variables, right? One is x, right? And x, this is the PMF of x. X takes possible values 3, 4, and 5. And discrete random variable y, and y takes values 1, 2, 6, and 8, right? So this is the PMFs. These are the PMFs of x and y, right? And with these PMFs, what we could do is we could form line diagrams, right? So what a line diagram is, so for example, for random variable x over here, right, at x is equal to 3, you have a probability of 0.3, right? So you use a line over here of height 0.3 to indicate that probability. And usually with these line diagrams, you put a little dot on top over here, right? Okay, so x is equal to 4 for for a random variable x, the probability getting value 4 is 0.4, and this would be this line over here. And similarly, you get when x is equal to 5, right? And the same way you form your line diagram for random variable y, right? Okay, so with these over here, right, what we could do is we could work out expected value of x and expected value of y, right? Remember, to calculate expected value of x, right, and I'm denoting it here instead of e of x, I'm denoting it as mu here of the x here. So mu over here is usually used to denote mean, right, of a probability distribution, and the x here is the random variable for which you're taking the mean for, right? So this is the same formula. Mu of x is the same as expected value of x, right? And how you calculate the expected value of x, as we saw already, is x times the probabilities, right? So it'll work out that the mean of a random variable x over here is equal to 4, right? And similarly, you could work it out for y. The mean of the random variable y in this case happens to also be equal to 4. Right. Okay, so I indicate that in the line diagrams, right? So in the line diagram over here, right, for the line diagram for the random variable x here, right, you see that the mean is equal to 4. And notice that your, your PMF over here is symmetrical about this 4 over here, right? The probability that you get x is equal to 3 and the probability that you get x is equal to 5 is actually equal, right? So what that means over here is, well, the probability is the mean over here is centered at this 4. It's probably easy to see over here because of the symmetry, right? Okay, so likewise over here, for random variable y, right, the mean is also 4, right? It's probably not that easy to see the symmetry over here, right? But if there is any symmetry, right? But here you see in that this probability distribution is centered about the 4, right? And now we want to go back to what I was saying a little earlier, right? Your variance, what the variance is doing for you, it's quantifying the spread of the values of x about this mean over here, right? So what you want to notice is for this random variable x over here, right? It is not highly dispersed about your mean over here, which is 4, right? You could have 3, you could have 5, but there's nothing else further away from this mean, right? It's only 3 and 5 over here. It's not to say that you have 2 or 6 or anything like that. The possible values about the 4 are just the 3 and the 5, right? Okay, on the other hand over here, right, here the mean is also 4, but what you see over here is that the possible values that the y can take, right? The possible values that y could take would be the 1, 2, 6, and 8, right? And these are further away from the mean than in the case of x, right? So the dispersion, the spread about the mean for y over here is greater than the spread for the x over here, right? And in terms of variance, right, well, the variance is in fact measuring spread about the mean, dispersion about the mean. So what you would expect is that the variance in the case of the random variable x would in fact be smaller than the variance of y, right? Because, well, you have more spread about the mean for y than you have for x. Alright, so I just said that what the variance of x is going to denoted by var x over here is denoting, it's indicating or giving you an idea as to what the dispersion is about the mean of a random variable, right? But let's see the actual definition, right? So the definition of variance of a random variable x is expected value of x minus mu squared, right? Okay, and you want to notice this is a definition in the discrete case and in the continuous case, right? It's just that in the discrete case you'd have a certain formula, and in the continuous case you'd have a similar but a different formula, right? So this is a definition of variance. The definition of variance is expected value of x minus mu squared, right? Where mu here, right, is the mean or expected value of your random variable x over here, right? Okay, so this, and in the discrete case, expected value of x minus mu squared, right? This is a function of the random variable x, right? And we saw how to get expected value of a function of a random variable x, right? What you do is you sum over the possible values of x, and you put your function over here, right, with the small x minus mu squared, and you're multiplying over here against your PMF, right? In the continuous case, right, right here again you have expected value of x minus mu squared. This is expected value of a function of a continuous random variable now, right? And we saw how to do that, right? This is the g of x over here, right? And you take in the big X, replacing it by small x over here. So your function is x minus mu squared over here, and you multiply this against the PDF, right? And then you integrate over all possible values of the continuous random variable, right? Which would be minus infinity to infinity, right? And as we saw before, right? If your PDF is just defined in a certain finite interval, this integral over here is going to simplify for us, right? Okay, so this is our definition of variance, and variance of x is denoted as var x and also as sigma squared, right? So if sigma squared is equal to variance of x, right? If I have variance of x equal to sigma squared, right? Then the sigma, right, which is the square root of the variance, that's called the standard deviation of x, right? Okay, so one more time, var x we can also write as sigma squared, and the sigma itself is just a standard deviation of x, right? So in other words, sigma is standard deviation is the square root of variance. Alright, so let's calculate variance of this random variable big X over here, right? Okay, so big X, the PMF of the big X is given over here. So big X has possible values 3, 4, and 5, and these are the probabilities here, right? And we saw already that you can illustrate the PMF of this discrete random variable on a line diagram here, right? Okay, so your definition of variance in discrete case and in continuous case, you need the mean first of all, right? So you need to work out expected value of x first of all, right? And I believe we did that already, but let's do it again, right? Okay, so if I want to calculate variance, right, because your definition of variance over here requires this mean mu over here, right? So I said I need to calculate, and mu over here is expected value. So I need to calculate that first of all, right? And this is my formula for calculating expected value of e of x, and I work it out over here, and I get my mean is 4, right? Okay, so now that I have that the mean over here is 4, right? Now I can use my definition here to calculate the variance, right? This is the discrete case. And what I have, x is a discrete random variable. Okay, so to calculate the variance of x, it's you sum in over all possible values of x, and you take an x and you subtract in the mean, and then you square it, right? And you multiply in by the probability. Okay, so you sum in over all possible values of x, and that's what the small x is doing for you. Okay, you have this x here, that value of x, and you're subtracting the mean, you're squaring it, and then you calculating over here the probability that the big X is equal to the X that you're indexing with, right? Okay, so we have in this case the mean over here is 4, right? So let's put that in, right? And then the possible values of X, right? 3, 4, and 5, right? Okay, so when X is equal to 3, you have 3 minus 4 squared over here, probability X is equal to 3. When x is equal to 4, right, so this value of your random variable, right, so you're going to have 4 minus 4 squared, right, probability x is equal to, times probability x is equal to 4. And then for the 5 over here, you have 5 minus 4 squared, right, probability times probability x is equal to 5, right? Okay, so what do you want to notice over here? Let's just look at this guy in the case when the x is equal to 3, right? So when x is equal to 3, what you're doing is you're calculating this quantity, which is 3 minus 4 squared, right? Now this 3 minus 4 over here, right? What you're doing is you measuring 3 minus 4 is in fact 3 minus 4 squared is the square of the distance between 3 and 4, right? So part of this variance over here is you calculating for each x over here, right? Each possible value of x. You're calculating its distance, right, from the mean, right? And then you're multiplying it by the probability, right? All right, and similarly for x is equal to 4, right? We use our formula here, right? So we put in the 4, right? We're going to get 4 minus 4 squared, right? So 4 minus 4 squared, which is 0 squared, times probability x is equal to 4, right? So for this, x is equal to 4, right? We calculate the term in the variance, right? Okay, and then the last one, when we want to calculate the variance for x, right, is you use when the x is equal to 5, right? So you're going to have 5 minus 4 squared, right, times probability when x is equal to 5, and the probability when x is equal to 5 is 0.3, right? Okay, so the 3 minus 4 squared gives me 1 squared times the probability, which is 0.3. The 4 minus 4 squared gives me 0 squared, which is 0 times the probability x is equal to 4. And then 5 minus 4 squared gives me 1 squared over here times the probability when x is equal to 5, right? And that the probability for that is 0.3, right? Okay, so your variance of x is the sum of these, and the variance of x is equal to 0.6, right? Okay, so let's also work out the variance of y, right? So to get the variance of y, using the same formula, but now the random variable is y over here, right? Your possible values for the y would be 1, 2, 6, and 8, right? For random variable y, we worked out that the mean of the random variable y is equal to 4, right? So we're going to be using that 4 inside here, right? Okay, and now we put in the values of the y, right? So the values of the y would be 1, 2, 6, and 8, right? And we put in that into a formula over here, right? So when we put in 1, we get 1 minus 4 squared, which is minus 3, and minus 3 squared is just 3 squared over here, times probability y is equal to y, which is 0.4, right? And you do that for each of these, right? When you put into 2, you're going to get 2 minus 4, which is minus 2 squared, which gives me this 2 squared, times probability y is equal to 2 is equal to 0.1, right? So I do that for the 1, 2, the 6, and the 8, and I get these 4 terms over here, and then I work this out, and I get my variance is equal to 8.4, right? Alright, so the variance of x we worked out to be 0.6, and the variance of y we worked out to be 8.4, right? So we've seen that the variance of y is bigger than the variance of x. And when you look at the line diagrams for x and y, right, we notice that the values of your random variable, the possible values for your random variable x, are closer to the mean over here for, right? And in the case of the y over here, the possible values for the random variable are actually further away from the mean over here for, right? Okay, so we saw that our definition of variance of x is expected value of x minus mu squared, right? Okay, so what we want is we want alternative definition for variance, right? Sometimes it's easier to work with this one, right? So here I have variance is equal to expected value of x minus mu squared, right? Where mu is the mean, right? So expected value of x, right? And my second formula that I have for variance would be this one over here, right? That says that variance of x is equal to expected value of x squared minus expected value of x, all to b squared, right? So you want to notice that in both cases you still need to work out what the mean is first of all, right? When you're doing your variance calculation, right? because over here and in these formula with the you'd need the mu, right? And the mu is the expected value of x, right? So you need to work that out first of all, right? So likewise over here, we also need to work out expected value of x first of all, right? Right, so let's see how this formula works, right? Let's get an idea of what the proof of it is, right? This is the proof in a discrete case. You can take a look at decking if you want proof in the continuous case, right? Okay, so we're doing it in a discrete case, and we're going to call the PMF of the discrete random variable, we're going to call it f of x, right? And the expected value of x, right, which is, this is typical, this is the definition for the expected value of x. The expected value of x is, we're going to denote as mu, right? Okay, so we want variance of x. We want to get this formula over here, right? But how we're going to get it is we're going to use our definition, right? So variance of x in the case of a discrete random variable is expected value of x minus mu squared, which is this summation over here over all the possible values of x, right? Of x minus mu squared times the PMF f of x over here, right? So that's this first line. And what you do now is you expand this out, right? Just using this is just squares, right? So this is x squared minus 2 mu x plus mu squared, right? And now what you do is you distribute the sum over here, right? So you're going to have, well, first of all, what you do is you take the f of x and multiply it by the x squared by each of these terms, right? And then you distribute the sum, right? Right, so over here I have summation of x squared f of x over all possible values of x, right? Here, with your summation, what I can do is I can pull out the mu over here, right? So I'm going to get minus 2 mu, right? Summation of x f of x, right? And then over here, what I'm going to end up with is mu squared times summation of f of x, right? Okay, now f of x is a PMF, right? And if you add up, and the PMF is giving you the probabilities for the values of the random variable, right? And if you add up all those probabilities, you'll get 1, right? So that's how you get this 1 over here. Right, this over here is summation of x times the PMF, right? But summation of x times the PMF is just the expected value of x, which is mu, right? So this, inside this bracket over here, it's mu, right? And this over here, what this is this is expected value of a function, right? The function x squared, right? Okay, so this over here, this first summation is expected value of x squared, right? So end up with this, right? And notice over here what I have is minus 2 mu squared plus mu squared. So overall, this would give me expected value of x squared minus mu squared. And remember, mu is expected value of x, right? So I get expected value of x squared minus expected value of x all to v squared, which is what I want. Alright, so we saw that expected value of function of a random variable, this would be how you would calculate it, right? If this is g of x, where x is the random variable, then in the discrete case, you're going to have the function g of x over here. And then you're going to sum over all possible values of your discrete random variable, right? So this here is the discrete case. And this is expected value of g of x in the continuous case, right? So you have your function g of x over here. And you're multiplying against the probability density function and integrating from infinity to minus infinity, right? Okay, so we saw examples of this already, right? Now what we want to look at over here is a specific example, right? So this section is, we're looking at linear combinations of random variables, right? So this over here, this is a linear function of the random variable x here, right? And these two specific formulae are fairly useful for us, right? So this is why we isolated them over here, right? Okay, so first one is expected value of aX plus b, right? When a and b are constants, right? So expected value of aX plus b is equal to a times expected value of x plus b, right? In other words, we can work this out. The expected value of aX plus b we can express just in terms of expected value of x, right? So if we already know expected value of x, then this is easy to work out, right? Okay, and likewise we have variance of ax plus b, right? And variance of ax plus b is equal to a squared variance of x, right? Right. In this case, you want to notice that variance of ax plus b doesn't depend on the b, right? The only thing it really depends on is the a over here, right? The reason for that is that the reason why your variance formula here doesn't depend on the b is if you consider ax plus b, right? So if this is an example of an x over here, right? So this is a discrete random variable here, right? The PMF of a discrete random variable, and this is the line diagram for it. Okay, so ax plus b, right? If you're looking at ax plus b, right? Well, what the plus b is doing for you is the plus b is a translation, right? Now, if you translate your random variable, right? Say this one shifted along to the right by 1 unit, right? What variance is doing for you is variance is measuring dispersion about the mean, right? Now, so if you translated x over here by b, right, what would happen is that the mean would shift, right? Okay, so you'd get the overall same pattern over here, and the dispersion about the mean would in fact be the same, right? So that's roughly why you don't see this b over here on this side when you're working out variance of ax plus b, right? You do, however, see the a over here, right? And what the a is doing for you is the a is scaling, right? So for example, if a is bigger than 1, what would happen is that your points over here will disperse, right? And if your points disperse, if a is bigger than 1, the points will disperse, right? And with a larger dispersion, you're going to get a larger variance, right? So in the case when the a is bigger than 1, you would expect your variance to increase, right? Anyway, so that's roughly what's going on, right? Let's prove this first one over here, right? That expected value of ax plus b is equal to a expected value of x plus b, right? And we're going to do it in the case of when we have a continuous random variable, right? And in the case of when we have a continuous random variable, if we want to get expected value of a function, right, if we want to get expected value of a function of a random variable, this is the formula that we're going to use, right? Now, in this case, the formula g of x is ax plus b, right? So the expected value of ax plus b, what I'll do is I'll put the ax plus b inside here, right? I'm multiplying by the PDF, and then I integrate from infinity to minus infinity, right? Now, this is an integral. Okay, so first thing what you're going to do is you're going to multiply this out. So you're going to have ax times f of x plus b times f of x, right? And then because it's a sum inside here, right, you'll be able to split it apart, right? And with an integral, you could also pull constants out, right? So that's how I go from here to here. Now, what you want to notice is that this over here, this integral of x times the PDF over here, this is nothing but expected value of x, right? When x is a continuous random variable, right? So you have a times expected value of x. And this over here, what you're doing is you're integrating your PDF all values of x. In other words, you're summing your probabilities. When you sum all the probabilities, you're going to get 1, right? So I get a times e of x over expected value of x plus b, which is what I want, right? Alright, so let's see an example of using these formula here, right? For expected value of ax plus b and for variance of ax plus b, right? Alright, so the example here is that there's a testing procedure, right? And the scores of this testing procedure is a random variable x, which is taken values between -5 and 20, right? And you're given the expected value and the variance of the x, right? The expected value is 10 and the variance of the x is 7, right? Now what you do is you're gonna apply a transformation to this x over here in order to standardize the scores, right? We want this -5 to behave like 0, and we want the 20 over here to behave like 100, right? So what we do is we use this new random variable y, which is in terms of the x over here, right? I notice when I have x is equal to -5, I'm going to get 4 times -5, which is -20 plus 20, which would give me 0, right? And then when I have x is equal to 20, I have 4 times 20, which is 80, plus 20 is 100, right? So what the y is equal to 4x plus 20 is doing, it's uh, transforming the interval from -5 to 20 to the interval 0 to 100, right? And it's doing it in a linear fashion like this. Anyway, so that's what the y is, but what we really want to do over here is we want to determine the expected value of y and the variance of y, right? And it's not hard in this case, right? All you're going to be doing is just using these two formulae here, right? Okay, so expected value of the y, right, using this formula here is expected anyway. So the y is equal to 4x plus 20. So expected value of y is expected value of the 4x plus 20. And this is linear inside here, right? And we're using this. So what we can do is we can split it apart. We're going to have the 20 over here. So the b over here is 20 and the a over here is 4, right? Right, and now all you do is you just put in what the expected value of x is, which was given to you, which is 10, right? And that gives me 4 times expected value, which is 10, right? Plus 20, so I get 60 over here, right? Okay, so I calculate the expected value of y using this formula here, right? And similarly, I can get the variance of y, right? So the variance of y is equal to 4x plus 20, right? So what we need is to work out variance of 4x plus 20. In this case, the a is equal to 4 and the b is equal to 20, right? And the variance of 4x plus 20 is going to be the a squared, which is 4 squared, times the variance of x, right? So notice the 20 doesn't play a part in this variance calculation, right? Okay, so I have 4 squared times the variance of x, and 4 squared is 16. The variance of x was given to me, which was 7, right? So I have 16 times 7, which is 112, right? So variance of y is 112. Right, so here's a not difficult exercise that you can do. Right, so given you the two results that we just saw, right, that expected value of ax plus b is equal to a times expected value of x plus b, and variance of ax plus b is equal to a squared variance of x, right? Use these two results to show these three over here, right? To show that expected value of ax is equal to a expected value of x. Expected value of b, so a constant is just a constant itself, right? And the variance of x plus b is equal to variance of x, right? And really you just use these by just choosing suitable values for a, b, right? Okay, so for example over here you could show this first one, you can just use b is equal to 0, right? Okay, so you can try these as an exercise. Alright, so we saw that if we have a random variable x, right, and we form ax plus b, right, then we can determine the expected value of ax plus b, right? So over here what you're doing is you start with a random variable x, and now we have this new random variable ax plus b, right? And this formula gives me expected value of ax plus b, right? Right, and you want to notice also that this is linear over here, right? Right, so now we have this result, which is analogous, right? I have x and y are two random variables with a joint probability function, right? Okay, and your setup here is that either x and y are both discrete or x and y are both continuous, right? Okay, so given the x and y random variables, right, with a joint probability function, right, what you could do is you could consider a new random variable, which is ax plus by plus c, right? And the expected value of ax plus by plus c, right, is equal to a times expected value of x plus b times expected value of y plus c. Okay. All right. Okay, and then for the random variable ax plus by plus c, right, we'd consider the variance of it, right? And the variance of it is a squared variance of x plus b squared variance of y plus 2ab covariance of x and y, right? So remember, this is our definition of covariance here, right? The definition of covariance, it's expected value of the product of x minus the mean of mu times y minus the mean of y, right? And this covariance of x and y, right, we could alternatively write as expected value of xy minus expected value of x times expected value of y, right? And you want to recall, if you're going to calculate your covariance, right, okay, what you're doing is this over here. If you do it this way, right, I'm using x minus the mean times y minus the mean, or you do it this way, right? In both cases, what you need to do is you need to use expected value of a function of x and y, right? In the case when x and y are jointly distributed, right? In other words, you're using these formulae over here, right? Which we talked about a little earlier, right? Okay, so for example, to get expected value of xy over here, then what you would need is you'd need x times y over here for the g of xy, right? Right, as a matter of fact, if you're considering this object over here, right, expected value of ax plus by plus c, right, how you actually calculate this and how you show this result is you're going to be using these formula here, right? One of these depending on whether it's two discrete x and y or two continuous random variables x and y over here, right? Okay, so this is what we use. In fact, this is what would be used to prove this result over here, right? This is expected value of a function of x and y in the case of when you have a joint distribution, right? All right. Okay, so, well, as I was saying, variance of ax plus by plus c is a squared variance of x plus b squared variance of y plus 2ab covariance of x and y, right? And you want to recall that if x and y are independent, then the covariance is going to be equal to 0, right? So in the case of when x and y are independent, this result over here will simplify, right? The covariance term will drop off, right? And what we would have is that variance of ax plus by plus c is equal to a squared variance of x plus b squared variance of y. So let's see an example of using these results here, right? Okay, so I have two independent random variables x and y, right? I'm given that the mean of x is 30 and the standard deviation is 0.05, right? In other words, the variance would be the square of this, which would be 0.05 squared, right? Okay, and similarly, I have the mean of y, right? And then the standard deviation of y, right? And now I'm considering a random variable as z is equal to y minus x, right? Okay, so notice this z is equal to y minus x is of this form over here, right? ax plus by plus c, right? In this case, in the case of the example, right, the a is equal to 1, the b is equal to -1, and the c is equal to 0, right? Okay, and what we want to do is we want to calculate the expected value of this z, right? And we want to calculate the variance of z, right? And what we're going to do is we will use this result over here, this first one, and then this third one over here, right? We're using this third one over here because we're given that x and y are independent, right? Okay, so let's work out first of all the expected value of z, right? So the expected value of z is equal to y minus x, right? So what we're doing over here is we're working out expected value of y minus x, right? And now what you do is you use this result, right, for expected values, right? Basically, you have a linearity property for expected values, right? So what you could do is you take expected values of the individual variables and then you can pull constants out, right? So here I can take expected value of y, take expected value of the minus x, and I pull the minus sign outside, right? Okay, so using this over here, I get expected value of z is equal to expected value of y minus x, which is expected value of y minus expected value of x. And now I just put in the information that's given to me, right? Expected value of y is 30.25, expected value of x is 30, therefore expected value of z is the difference of these, which is 0.25, right? Okay, and similarly, we use this formula here for the variance to calculate variance of z, right? So z again is y minus x. So I'm working out a variance of y minus x, right? So what I'm doing is I'm using this formula over here, right? Remember that x and y are independent given in the problem, right? So I use this version here. I don't use the one with the covariance. Okay, right? So the x and y are independent. I use this version here. Uh, right. You have okay. So you have two random variables over here, right? One added to the next one. The coefficient of the x over here is -1, right? So if you forget about the c for the time being, if you have a sum of two random variables, ax plus by, right? What you're doing is you're taking the coefficient out in front here and you're squaring it. And you're taking the coefficient out in front here for the y and you're squaring it, and then you're adding them, right? So likewise over here, the coefficient here for the y is 1, so you put that out in front, that's 1 squared. And times variance of y, and then plus, right, this coefficient over here, which is -1 squared, right, times variance of x, right? Okay, so I get this, right, using this formula. Notice here the x is before the y, and here the y is before the x, right? But it's not really a big deal, right? You could call it x, you could call it y. It doesn't make a difference here, right? Okay, the main thing is that you just keep track of everything, right? Alright, so I have from this that variance of y minus x is equal to 1 squared variance of y plus -1 squared variance of x, right? And you want to remember that variance of y is the standard deviation of y squared, and the variance of x is standard deviation of x squared, right? And the standard deviations were given to me, right? Okay, so therefore variance, this one over here, which is the variance of y, is this 0.06 squared, right? And then the variance of x you get by squaring the standard deviation for the x, so the 0.05 squared. And then you just evaluate this, and this gives me my variance of z over here, right? 0.0061. Okay, so this result over here is expected value of two random variables, the sum of two random variables with constants out in front over here, right? A and b, right? Okay, and how you get in the expected value of these is taking expected value of the x multiplying it by the a, taking the expected value of y multiplying it by the b, and then adding them, right? And then if you have a constant c, you take expected value of the constant, and the expected value of the constant is just the constant itself, right? Okay, so this is in the case of when you have two variables, x and y, right? But you could have more than two variables, right? Two random variables, right? You can have say up to n random variables over here, right? And again, now what we want to do is we want to consider a linear combination of the random variables, like how over here this was a linear combination of the x and y, right? Linear combination, it just means that you take linear combination of x and y means you take x and you multiply it by a constant. You take y and multiply it by some constant and you add them, right? So likewise over here, I have x1 multiplied by a constant that's called a1. I have x2 multiplied by a constant which is called a2, right? And so on up to xn, right? xn I multiplied by a constant an. And then I'm adding these, right? So this is a linear combination of the random variables x1, x2 up to xn over here, right? Okay, now how did we work this one out, right? How we work this one out is basically you just take an expected value of just the variables themselves and you pull in the constants out, right? And notice we're doing the same thing over here, right? Here you just take expected value of the x1, take expected value of the x2, and up to expected value of the xn. And you multiply each one by the corresponding constant, a1 over here, a2 over here, and an over here, and then each of these you add it up, right? Okay, so this over here is a more general uh, description or more general result than this one given over here, right? Okay, you do want to notice over here I don't have a plus a constant over here, right? This is just sum of random variables. Here, this has a little extra information over here where you allowed add a real constant over here, right? In this case, you don't have a real constant, but aside from that, it's a similar result, right? Okay, and likewise over here, and now we're dealing with random variables being independent, right? The x1, x2 up to xn are independent, right? Okay, and if remember this case over here, if I have x and y independent, then I have a formula for variance of ax plus by plus c, right? And let's just assume that the c is going to be equal to 0 because we have no constant across here, right? And if the c is equal to 0, what you're going to have is variance of ax plus by is equal to a squared variance of x plus b squared variance of y, right? So notice inside here what you have is a sum ax plus by, right? And likewise over here you have this linear combination a1 x1 plus a2 x2 up to an xn, right? Okay, so the form inside here is similar to the form inside here, right? And you want to notice, well, what's the variance of this linear combination? It's a squared variance of x plus b squared variance of y, right? And similarly across here, how you what the variance of this is going to be is you take variance of the individual random variables. You take coefficient in front here, for example the a1, and then you square it and multiply it by the variance of x1. Likewise, this coefficient a2 over here, you square it, you get a2 squared, and you multiply it by the variance x2. And then up to the an squared variance of xn, right? And then you add all those together, right? Which is the same thing that you're doing over here, right? So this is in the case of when you have two independent random variables, right? And in this case over here, you have up to n independent random variables. You have n independent random variables, right? So really, this formula over here is just a generalization of this one, right? Assuming that in this case, the c is equal to 0.